All right, so I have to hurry up. You're the lucky ones, because usually the original version of that slide deck was 270 slides. Was a little bit too much for 45 minutes, so I reduced it to 167. That worked for 50 minutes, so this is just 157 slides. It was 67 last week, so we will see. First of all, no, let's start. My name is Gerrit Grunwald. I'm working for Azul. We do JVMs. And if you would like to know more about me or whatever, get in touch with me. I will be here afterwards. There's an apero, as far as I know. Memory management in the JVM. It's automatic, right? So why care? Why this session? Who of you sets a specific garbage collector in production? See? That means the default works for most of you, right? Who's using JDK 8 or below in the audience? In production? 1, 2, okay. 11? 17? 21? Okay. 23 someone? No? Okay, so yeah, it has an impact on application performance, memory management, and obviously application responsiveness. We will come to that. And also on system requirements like memory consumption and these kind of things. So, and if we take a look at it, how it works, I hope it's readable. Probably these both screens will be better than this one. We all start with a so-called stack frame that's bound to a thread. So every thread gets a stack frame. In the stack frame, which can grow and shrink dynamically, we store primitives and references in the JVM. And this is local access, so this is thread safe. So we don't have to do garbage collection and this kind of things. And then we have the heap. And in the heap, we store objects, right? And this one has shared access, so we need to do garbage collection. It's not thread safe. And then there is the metaspace, which contains information about class metadata, consent pool, method bytecode, and so on. This is, for this session, not really important. So in principle, everything the JVM needs to run to handle classes. And this one is also no fixed size, so it grows dynamically. As far as I know, it can't shrink, but I might be wrong here. So we only focus on heap and stack, right? To give you a little example and try to explain how it works, and keep in mind, this is not the detailed thing. This is not a deep dive on garbage collection. This is all the most simplest way to give you an idea. So we have this little program, a record of person with a property name. I instantiated 4 of them, put them in a list, print out the first one, which is my name. Okay, fine. We get a stack frame for this one, for this thread. And we have all the references for these objects in here. And then we have the heap, where we have the actual objects stored. And we have references pointing from the stack frame into the heap, right? That's important. So that means this stuff takes up memory on the heap, and you see the references. You see the list has references internally to these objects too, because they are stored in the list. That means all this stuff is reachable. That's important. So we can reach it from the stack, which is the roots of everything. We can reach it in the heap. Okay, so now I set the first person to null. If I would print out P1, it's null. But I can still reach it, because it's still in the list, and the list has an internal reference to the same object. So if I type in this code, you will get the same result, even if the object is set to null. Some people forget that. If they set objects to null, they think, oh, they're gone, will be garbage collected. Yes, if they are not somewhere in some collection, right? So I have to keep that in mind. If I then set the list to null, it's gone. So then we only have these 3 references or objects that are still live, because they are reachable. We speak about live objects when I can reach them from the stack, right? And you see, there was a reference from here to the list, then from the list to the objects, and it could be a whole tree of references within the heap. Okay. That means these objects, the red ones here with the red arrows, they are just garbage. They're lying around still on the heap, are not reachable. The question is, how can I get rid of them? Right? So this is garbage collection. That's the very basic idea of garbage collection, is to clean this stuff up. And it's a form of automatic memory management. There's also automatic reference counting, which is, for example, used in Swift. There's no one is better than the other. It's just a different approach. And it's made to identify, reclaim no longer used memory. It's made for efficient memory utilization. And most of all, to free us as a developer from this need to manage memory manually. No malloc, no free. Right? So this is done by the JVM. Which sounds good. If you know how it works, it is good. But sometimes it's like, oh, garbage collection. Yeah, I have that. I have no idea how it works. I just trust it. To get an idea, usually we talk about different phases when we talk about garbage collection. So, and this is just for precise collectors. There's also conservative collectors. But we just, because this is the majority in the JVM, so we start with one phase, which is tracing. That means finding objects on the heap that are live, that I can reach from the stack, starting from the stack, following all the references. I need to reach them, then they are live. This is the tracing phase. And then we have to free up all the other stuff, so the stuff that I can't reach anymore, which is the freeing phase in this case. And then there's another one which is called compaction, because from time to time we have to compact the heap, right? But we will come to that in a little demo. So who remembers Windows 3.11? Disk defragmentation. Yes, we will see that, because this is exactly what it is. But before we go there, stopping the world, who knows what stop the world means? It's no problem if you don't know. It's just because people talk about it, and you will hear that quite often. Stop the world pauses or STW pauses and stuff like that. So what it means is we halt, or we stop all application threads in the JVM, and then we do the garbage collection. And how that works is we have application threads running, and then there's a signal from the JVM, which is a JVM save point signal, which is sent to all the threads. That means stop. Sometimes takes longer, sometimes not. Once all the application threads stopped, we reach a so-called JVM save point. That means all threads are safe now. Now we can do garbage collection. So then we do the garbage collection, either with one thread or multiple threads. When this is done, then we continue running the application threads. And this orange pause, that's the stop the world pause. And it can be, depending on the application heap size and the garbage collector, it can be up to tens of seconds. So we saw that. So the application just stops. Nothing is happening. You can't press buttons, no responses from REST endpoints, because it literally stops. Once it finished the garbage collection, it will continue. That's stop the world pauses. And you don't want to have that, right? If you have a web shop, you don't want to, customers like, buy it. Doesn't work. Okay, I go to Amazon. Yeah, okay. Collectors. This is not the garbage collectors we have in the JVM. That's the principles that are available here. Nice. So we start with the so-called non-moving collector, and you will directly see why it's called non-moving. This is mark and sweep. Who heard about mark and sweep? Okay, pretty simple. This is, like you know from Windows 3.11, that should be the heap. To make it as simple as possible, every object that I allocate space for is one memory cell, here in my example, okay? And this is the gray ones, that's free cells. When they become blue, they have been allocated. That means they are live. If they are purple, they are dead. So it's like something was set to null, you return from a method, then everything that was in the method defined automatically is dereferenced. If they get this little red square in the upper left corner, that means the garbage collector marked them as live. So the tracing phase, he finds everything, marks it, and then he removes the old ones, the purple ones. If they have a number, that means you have objects that are live, the garbage collection cycle ends, and then you increase this number, because it survived one garbage collection cycle. Right? So the higher the number, the older the object. That's the idea. So let's have a look. So we start allocating, and you see objects die fast. So we fill up the heap, and once we reach the end, we will stop the world, mark the live ones, tracing, remove the rest, and then continue. So stop, mark, we increase the counter, we continue. You can already see what happens, fragmentation. And you can imagine it gets harder and harder. This is the simple example. Each object takes just one cell. If I have a large object, it gets harder and harder to find space to fill that object in, right? That makes the whole thing slower. So that's something you would like to avoid, but this is a non-moving collector. We don't move things around here. No compaction. We just use the stuff that is available. This is mark and sweep. And it is in use, so it's not really a bad collector, but has its drawbacks. And now my clicker again doesn't work anymore. Oh, okay, strange. Yeah, fragmentation is the problem. That leads me to moving collectors, because we have two different ones. We have a so-called compacting collector and the copy collector. Let's start with the compacting collector, which is mark and compact, which is in principle the same that we saw before, same thing. One additional step, so we go through the procedure, we allocate memory, we run out of memory, we mark the live cells, free all the dead cells, and then we unmark live cells. That means we remove the little square, and then we compact everything to the left, right? To be able to do compaction, we can't really fill it up completely. We need a little bit of space on the right side to be able to copy stuff first before we move stuff to the other side. This is a so-called headroom. Let's take a look at this one. Same thing. We fill it up, objects die, and I think it will start here. I left the last column free. Let's see. Stop, mark, remove, unmark, compact. And now compact. Now we start again. You directly see the advantage. We always can allocate freely because there's always free space ahead. So that means fast allocation, which is good. This is something we aim for. It's always fast allocation. Makes your code faster because you don't have to look for free spaces, right? So again, stop, mark, then unmark, compact, continue. So this is mark and compact. This is still in use in some of the collectors. But you can imagine to free stuff, for example, it looks easy because this is just an example that I coded. But in reality, freeing means we have to go to each of the cells and check, is it live? Is it dead? Is it free? If it's dead, remove it. If it's live, keep it. The larger the heap will be, the longer it takes to do this kind of collection, because this freeing, right? Because we have to do that for all of them. And when we move things around, like we copy stuff, it's fragmented. We copy it first here, then we copy it back. We have to update all the references. Remember, there are pointers coming from the stack frame into the heap to each object. When we move it around, we have to update the pointers, the references. This also takes time. So this is the drawback of this collector. We need a little bit of headroom depending on the heap size, and we have to update references because it's moving. Leads me to the next one, which is the copy collector. Mark and copy. This one looks different. This looks like this. Instead of having just one space, we have two. Same size. One is called the to space, the other is the from space. And these spaces will toggle. Every time I fill up one space, I will toggle them. The from space becomes the to space, and so on. Apart from that, it's pretty much the same procedure, except we fill this space up first. When it's full, we stop, we mark, and then we copy all the marked live cells to this space. And what happens then is, then we know here is nothing more which is live. So we can directly remove the whole space at once. We don't have to check every cell. First advantage. Second, because we always copy to a free area, it's always compacted, right? Let's take a look at that. You will get the idea when you see it. So we fill it up, as usual. Once we reach this cell, stop, mark, copy, clean it up, and continue. So stop, mark, copy the live, clean up the left side, continue on this side. It's always compacted. Now the same on this, and you realize it will change colors. It changes from to space. Stop, toggle, now mark, copy, continue. So we always have a compacted area on the new space, and the freeing is way faster here, right? And with this we have fast allocation, and we can simply free the former space. The drawback is, if you have long-living objects, you copy them all the time until the end. If you have an object that you use for the whole lifetime of the application, you have to copy it with every garbage collection cycle, means also updating references all the time, okay? So the other disadvantage, you see it already, if you have a big heap, you need twice as much to be able to, in worst case, copy the complete heap to the other side, right? So this is the drawback of the copy collector. This is also in use, which leads me to generational collector. This is generational, mark, and compact. And you will see this is now a little bit different. And to give you an idea how it is created or structured, we have to go through the weak generational hypothesis. That means objects die young. Not only in Java, this is everywhere. And the reason for that is a simple example. You have a method. You create some variables in that method. When you call the method, you create the stuff, so you will get objects with references on the heap. Once you return from the method, everything that was defined in there is garbage. That means these objects only live for the time of the method call. So you create a lot of new objects all the time, and they directly die afterwards. It means this is usually the chart that you see. We have lots of short-living objects, a little bit of medium living, and then very few long-living objects. This is how it looks like. And to cope with that, we can structure the garbage collection for this by using different spaces, like an Eden space, where we create objects. And because they die fast, it doesn't have to be a big space. It can be a small one. And then we have a copy collector that we use for the so-called survivor spaces. Here we only copy stuff that survived in garbage collection in Eden. We copy it here. And then to avoid copying things all the time, there's the threshold. For example, in my demo here, I use, if it was copied 3 times, I promote it to the next space, which is the so-called to-nerd space. So this is how it looks like. So you might wonder, if I just have a few long-living, why is the to-nerd space so big? The reason is, it takes a long time to fill it up. The drawback is, once it is filled up, garbage collection will also take longer, because this is a huge area, right? So, and we talk about, do we see it already? No? Okay, young generation, because these objects will be created quite fast, don't live for a long time. So that's the young generation, and this is the old generation in the to-nerd space. And when we talk about collections, then you already see we have different collectors here. This is, for example, a mark and compact usually. This is the copy collector. This is also, I think this is just mark and sweep in the Eden. We talk about a minor collection in the young generation and a major collection in the to-nerd space or the old generation. And if we do both, then we talk about the full collection. Sometimes people mess that up and say, oh, it's a full collection, it's just this one. No. Or major collection is both. No, no. Major, old generation, minor, young generation. Full collection is both. In my example, I do a full collection. And it's smaller, so you already know what will happen. I fill up the yellow one. Stuff that survives will be copied to the copy collector, the survivor spaces. When they survive 3 times, I will promote them to the to-nerd space. The interesting part, we look at that until we promote some of them, and then I do a fast forward. And then you will see some kind of wavefront moving to the heap, to the to-nerd space, to the old generation, because even in the old generation, these objects will die at some point. That means you have lots of old objects coming here slowly until we fill it up, right? And once we fill it up, we do a full collection. Let's see. Once it started, yeah. So we allocate, stuff will die, stop, mark, copy, continue, and so on. Once one of these objects, or some of them, survive 3 of these cycles, we will copy them or promote them, that's the name, to the old generation. And after that, it will be faster, so we don't have to wait, because that takes some time to fill up the to-nerd space here. Oh, now it goes. And now you see, now it gets faster. And now you see already the wavefront starting here. And this stuff moves slowly until we reach the end here. This is not really correct. There should be a little bit of free space, because this is mark and compact. Once we reach the the end position. Now it's slowed down again. At the next stop, there's no space to copy, so we do a collection here first. Mark, compact, and then we copy everything from the young generation into the old, and then we can start from scratch. Right? This is how a generational collector works if it's structured like this. It's not that complicated, but I think you get the idea. And if I'm right, the threshold here is 32 in the JVM for the copy collection in the survivor spaces. So objects need to survive 32 garbage collection cycles before they will be promoted to the inert space. So this is a quite good collector. It works for many things. We can fast allocation, don't have to copy long-living objects for too long. The only drawback is if the old collection gets big and it fills up, this garbage collection might take longer. Okay, that was all the simple stuff. What about concurrent collection? Because here we stop the world. If we talk about concurrent collection, and concurrency is hard, then it's a different story. So remember what I told you. We fill up the space, we stop, nothing happens on the application side, then we mark stuff, we find a tracing. And if we do that concurrently, and now it's a little bit of a different scheme here, we start again from the roots. This is the stack frames. There's a reference into the heap, and then in the heap we just follow all the reference that we can find, right, that are live. So first thing, we find that one, mark it as reachable, and then mark it live. So next one, reachable. Oh, because it's concurrent, no stop the world. The application can still change stuff now. So now the application decides, you know what, this reference I don't need anymore, I just remove it. And instead of using that one, I just create a new one here. The problem is the garbage collector is already here. He marked this one as live. He doesn't know anything about this cell. Okay? So what will happen? It will crash. So collector will continue, has no idea that there was another new reference, and it will break. How can we solve that? Well, there's something called like barriers. Did someone ever heard about the read barrier, write barrier? This is one example how you can use it. To make it as simple as possible, a barrier is a piece of code that will be executed every time you read or you write to a memory cell. Right? Depending if it's a read barrier, then when you read it, writing when you write it. And you can use that to track intergenerational references. Remember, there was the young generation on the left side, the old generation on the right side. There have been different collectors, right? Like the minor collection and the major collection. If I have now a reference that comes from the blue area back into the yellow one in the young generation, and I do a collection in the young generation, then the collector doesn't know about that stuff. Because it only checks the young generation. It doesn't know about the references coming from the old one. To keep track of that, you can use barriers. You can also use it to synchronize between the mutator, which is the allocator, and the collector. Right? This is the principles. One thing you have to keep in mind, if you use read barriers, they have to be extremely performant, because we have usually 75% reads, 25% writes in applications. So that means if you hit the read barrier so often, make sure it's as fast as possible. Back to the example. Now we start again at the stack frame, but now we install a write barrier every time on each of these objects. And what happens now is when the application thread removes this reference, in this example, the code that will be executed in the write barrier is every reference that was removed, mark this one as reachable. Right? This is the write barrier that we use here. So that means the collector still has no idea. There's a new reference. This will now be marked as reachable by the write barrier, and then the collector continues, right? It just collects stuff. But now the new thing is there's a so-called remarking phase. After it finished the first run, it will stop the world and then will only look for this reachable cells that have been marked in between. We'll find it, mark it, and then they are live. This is how a write barrier works. It's a little bit complex, all this stuff, so you don't have to remember all these things. Just keep in mind, barriers are used to execute code before you access the memory cell. That's more than enough. The next thing, this was marking, right? Just mark, find the live ones. Next thing is, if we would like to copy things around in memory while the application is running, how does this look? If we do stop the world copying, that means the stuff that we saw before. So we have an object that sits on the heap. We have references from the stack frame to that object. We copy it. Before we copy, we stop the world. Nothing happens. We can simply copy everything to the new location. Then we install a forwarding pointer in the original header of the object here. And then we can update all the references by just going through them. Once all the references are updated, we can just remove the original object and continue, right? This is stop the world, easy. If we don't stop the world, we do exactly the same. We take the object, we don't stop the world, we simply copy it. Now we start updating references. Okay. Well, the problem now is both of these objects suddenly are reachable on the heap because we don't stop the world, right? So that means application threads will still access them, and there's no one who can tell the application which is the right object here. So what happens is threads will access, depending on how far we are in updating the reference, it will access both objects. And this is a no-go, right? So that will break. So we have to do something. There is one solution that I will just explain to you. It's a so-called Brooks pointer. And this is a pointer that you install in front of the original headers object here. And all the references point to this pointer that we have there. And it points to its own header. Very simple. Now we copy the object. But before we now start updating references, and we install the pointer like this. This one points to this header, okay? Now before we update all these references pointing to the new location, we do an atomic update and we install this one. This is atomic, that means we don't have to really stop the world here. This pointer goes from that one to this now, and now we update references. That's the idea behind it. If we now do it, doesn't matter where the thread tries to access, it will always make sure that only the new object will be addressed. This is in principle how a Brooks pointer works. And then again, once we updated all the references, we can remove the old object. But this is also something you have to keep in mind. The old object we have to keep it in the heap until all the references have been updated, because the forwarding information is in the old object. Okay? Okay, so done. Easy. Not really, but you get the idea. Now let's start with collectors in the JVM. Oh, we're running out of time. Serial collector, simplest one. It is good if you have small nodes. Who's running Kubernetes? Or whatever orchestration system, containerized systems, services, okay? Who runs very small services? One CPU, maybe, less than 1.8 gigabytes of RAM? If you do that, you will get this collector if you don't define anyone. The JVM decides for you that if your system only has one CPU, or if it has less than 1.8 gigabytes, it's not a server for the JVM. This is back from the days, right? That means this is not a server, you get serial GC, if you like it or not. Doesn't mean it's a bad collector, but just to make sure, if you don't set something specifically, the JVM will choose this one. And this is how it works. We have the application threads, then we stop, and then we have one thread that does the garbage collection. Because we just have one CPU, right, in worst case. And then we continue. Okay. This is how serial works, and keep in mind, if you have a single node with a single CPU, and you don't specify the garbage collector, this one will be picked, or if you have less than 1.8 gigabytes, then also this one will be picked by the JVM. All right, leads me to parallel, which is someone using parallel GC here? No one. That's the so-called throughput collector. It's quite old, it's available in all JDKs, but it's the more or less fastest one that we have. It is not concurrent, and the trick here is It's good for multi-core systems if the heap is not too big. That means it's perfectly suited for small nodes, let's say up to 4 gigabytes of RAM. You maybe have 2 CPUs, perfect collector. If you can live with pause times, because that might happen with this collector. But for batch processing, there's nothing better than this one. Even not ZGC and all these things. This is a really good collector. It was the default garbage collector from JDK 5 till 8, and this is how it works. And you see the difference. Instead of having just one GC thread, we have multiple. And that makes it so good, because throughput means time you spend in garbage collection versus time you spend in the application. If you use lots of threads for garbage collection, of course, the pause time is short, right? So that makes a really good collector for these kind of nodes, so smaller ones. CMS, concurrent mark and sweep, this is more or less, it looks like the collector that I showed you, the generational one. That's very much the same, but this is per thread, so it's more complicated, of course, but this is how the memory is structured. That was good for, because I say good, you see already it is not available anymore. If you are on 17, it's gone. It was deprecated in JDK 9, it was removed in JDK 14. The reasons have been that it ran into allocation stalls and stuff, so it was not really always good. But they aimed for keeping the pause times shorter than 1 second. And that was a big step when you came from parallel or serial GC. I don't go to the diagram, but you see it's already more complex. It can do partially concurrent marking and concurrent sweeping. That makes the whole thing quite complicated. But it's deprecated, not available anymore. So leads me to G1. Everyone that is on JDK 9 and upwards, you use this one if you don't specify the default. And this is different. This is a so-called region-based collector. So we don't have these big chunks of memory anymore. Now we have so-called regions. And you see it on the left side, the region size depends on the max heap size that you define. So if you specify heap size that is smaller than 32 gigabytes, you get 8 megabytes of region size. This is one region, this one of these squares. And then we have these memory cells inside. This is just for the demo. This is the empty heap. This is how it could look like if we run it. We have Eden regions, we have survivor regions, and we have tenert regions. Right? We have multiple ones. And you can define all these size of these regions, which has an impact on the performance of your garbage collector. There's also a so-called humongous region. If you have an object that is bigger than half the size of the region, you will directly get the region, or if you need more, you get the whole thing completely. That also means if your object is just this size, let's say 75% of this size, the rest is empty. If you have lots of humongous objects, you might lose some memory, right? You have to also keep that in mind. And humongous objects means this is in principle directly to inert space. They won't be copied around because you don't want to move around big stuff in memory. So, I have an example, of course. I use 6 Eden regions, 6 of the yellow ones. When we run out of this space, out of the 6 ones, I take the 2 with the most garbage first. Because in this, if I have a lot of garbage, means I just have a few live objects. That means it's very quick to copy these new live objects to a survivor region, right? This is the idea. Let's take a look. So we allocate. Okay, next one. Regions can change. So this doesn't have to be an Eden region all the time, right? Or you see stuff will die. 6 ones full. Copy those to the survivor spaces. Now we continue until the survivor spaces fill up. And I think I have defined 3 survivor regions. So that means if 3 fill up, I will promote them to the tenert regions. And you see, by this region-based approach, it's way more flexible. And it's very cheap to clean up these regions because they are probably small. It's not like you have 1 terabyte of tenert space that you have to clean up. But this is only maximum 32 megabytes in one region, right? Which makes it faster. So I hope you get an idea how region-based collectors work. This is a different approach on doing it, and all the new collectors work like this. It's just how they define the regions is different. But this takes forever, so I continue. The pause time that G1 is aiming for is 200 milliseconds. It can be faster. If you tune it correctly, you can get down to 100, sometimes even faster. So this is the reason why it's a good default collector, and it seems to work for most of you. The sweet spot is between 16 and 32 gigabytes. Below that, it's okay, but the best performance you get if your heap is between 16 and 64 gigabytes. You see already, if you run microservices with just 4 gigabytes of RAM, think about parallel GC. Might be faster, so you have to give it a try. Okay, again, you see the diagram, way too complex. It's the default since JDK 9 and probably will stay there for some time. It can do partially concurrent marking and sweeping, so it has this concurrency in there. Then there is epsilon. Who knows that? Heard about it? Nobody. Okay, because that's the no collector collector. It's not a garbage collector. That's crazy, right? Why can I specify a garbage collector that doesn't do garbage collection? Because if I, for example, have a very small microservice and I know exactly how much memory this service needs or uses at runtime, there's no need for garbage collection, okay? So that means this is the best thing you can do. With the biggest problem, because if you run out of memory exception. There's no garbage collection at all with this one. That means you can use it for extremely short-lived jobs. If you really need the last drop latency, then this is perfect. But the hard part is, believe me, figuring out how much memory your application needs. If you have very small microservices, that's probably easy. If you work on a monolith or application server, forget about it, because you never know. It's terrible, right? So it's really, but for playing around with stuff, if you would like to test only the application performance without having garbage collection in there, and it's possible to do it with parts, then you can use this collector. It's available since JDK 11, and it's only in OpenJDK, which is also true for all the other collectors. But in OpenJ9, which is the one from IBM, they have similar collectors. They have different names, but some of them are similar to the ones in OpenJDK. Next one is Shenandoah. Someone ever heard about that one? It was developed by a Red Hat, Roman Kenke. Had a big part on that one. He moved on to Amazon, which might be the reason that this is the only collector in OpenJDK that is not generational. All the others are generational. This one not. Why would you like to have a generational collector? Because objects die young. That means if you have a young generation, you can collect them very often. And that means you can, later on, you can free space and allocate fast. With this one, you always have to do all of the memory, right? There's no generations here. So which is a little bit of a drawback for this collector, but still, I think they predict or they guarantee response times between 15 up to 15 milliseconds. That's the largest one. And you can use very large heaps in the hundreds of gigabytes. All right, so this is good for latency sensitive applications, large scale system, and so on. Yeah, you have a little bit of a reduced throughput with all the concurrent collectors. Keep that in mind. No one of you is Netflix. None of your companies, I bet. Because they switched to ZGC completely, and they said, it's awesome. We just saw 3% performance drop. Yes, it's a customer of ours, so we know what they are doing, and it's impressive, but just keep in mind, the performance will drop by 3%, and I will come to ZGC. So use the right collector. This is an advice. So, and there we go, ZGC, Z garbage collector. Again, a region-based. Here you see we only have old and young. There's no survivor spaces here, no homologous regions. It's just old and young generation. That's all. This one guarantees response times below 1 millisecond, right? So this is very fast. You might think, wow, it's a perfect collector for my application. Well, this one needs CPU and it needs memory. So you can't run it on one CPU or two CPU systems with 2 gigabytes of RAM. It will work, but believe me, G1 will be way faster. Parallel GC probably even faster. This one shines if you work with 100 gigabytes of RAM, 20 CPUs. This is awesome. There's nothing better than this. But if you have smaller things, it's not the best collector. And it came first as a non-generational version in JDK 15, and with JDK 21 we saw now a generational one, and this is also now the default. The non-generation is already deprecated, so it won't be further supported in the future. Okay, you see the overhead, CPU overhead, 10 to 20%. It could be, right? Keep that in mind. So it is a great collector, but not for everyone. It might become the default collector in the future. I heard some rumors, not sure if that is a good idea. And the non-generational version will be deprecated. I won't go into details with this one because this is a copy of this one, which is C4. This is the collector that Azul invented more than 10 years ago. And it looks like Oracle found the paper because it's publicly available and just did it on their own. It's exactly the same algorithm, and the non-general version is a one-to-one copy. It's exactly the same. The generational one is a little bit different. So this is only available in Azul Zing, and we use only read barriers. Everything that I say now also applies for ZGC. We name it loaded value barrier. If you look at ZGC, it's the colored pointer. That's how they name it. Same thing, same principles, all the same. You need, if you're on Linux, transparent huge pages helps a lot because that makes the memory page bigger, gives them more power. And I will just shortly explain two phases. Marking phase, because that's different from the other one that we saw. We have garbage collection threads. They go to the stack frames, find the live objects by following the references, okay? Same story, they mark them as live. This is all done by this LVB, loaded value barrier, which is a read barrier. And in our case, it's just one CPU cycle, so it's very fast. So now, we marked all this one. The lower right one, suddenly, the application allocates this cell. And now the difference here is, once the application thread triggers the loaded value barrier, this code will mark this cell. It's no need that the garbage collector has to do it. The application thread can mark cells. And then it will hand over, just the test and jump is the one instruction. It will hand over this information to the garbage collector. And then the garbage collector doesn't need to do this remarking phase that we saw with the other one, which makes the whole thing faster. So you see, a barrier was used to communicate between the application and the garbage collection threads in this case, which makes it quite fast. The other one, and this is the last one, I promise. Yeah, we have just a couple of minutes left. A so-called quick release. And that's quite interesting. And the same is for ZGC. So we don't work really on physical memory, right? We work on virtual memory, which is so-called memory pages, and we call the process paging. We have physical areas in the memory, and then we have virtual ones that will be mapped to the physical ones. So in this case, the purple ones are the physical memory. The virtual ones are the other ones you see already. It's an Eden space or whatever region. So now I copy things because I do compaction. I copy the first object, and instead of now installing the forwarding information in the old object, I just install it in a totally different space. I install it in an off-heap memory area, and that's always the same. That means the forwarding information is not anymore in the old object, but it's in a totally separated space. And that gives us the opportunity, once we move the second object, we can directly release the physical memory below, because we don't have to update references here. The information is still available, and the loaded value barrier will make sure that if now the application accesses this thing, it will automatically, and it won't find it, it will automatically look up the information in this area because this is fixed, and then it will update the reference automatically. So this is done as soon as something is accessing the object. And so with this, you don't need this stopping the world and stuff. Okay, that continues. Okay, yeah, you got the idea. This is the same as for ZGC. If you need very short response times, below 1 millisecond, I think the customer with the largest heap that we have has a 21 terabyte heap. And we can still do garbage collection below 1 millisecond, even with a 21 terabyte heap. So this would also work for ZGC, because it's the same. The only advantage that we have is we don't really see the performance overhead because in our Zing JVM, we wrote our own compiler, which creates faster code than the OpenJDK compiler. And with this, we can keep up and even have better performance than OpenJDK. That's the difference. You see the diagram way too complex. Okay, I will hurry up. Which one to choose? We have 3 criteria: throughput, latency, resource usage. So you can't choose all 3 of them. To make it easier, choose 2. This is how it works. If you don't have a lot of resources, but you need very low latency, sorry, throughput will be low. If you need high throughput and very low latency, sorry, you need more memory, right? This is how this diagram works. Make it easier for you is this. If pause times for you are no problem, go to the right side, right? If you need very short pause times, you can look to the left side of the diagram. And because everybody of you said you don't choose it, it seems you are quite good here in the middle somewhere. But this helps to choose the right one. And to make it easier for you, I'm not sure if they collect the slides. I created a little overview where you have all these collectors with their different properties that might help you to choose. So the most important part is I can't tell you which is the right garbage collector for your application, because you need to know how much memory does your application use, how many CPUs do you really need, these kind of things you have to monitor, and then you have to make a wise decision. That's how it works, right? And this might help you with this. I have no idea. But that's it. Thanks, and if you have questions, I will be around. Just come here and we can talk about it. Thank you.